Thank you. Yeah, our next speaker will be Oliver, who's the CEO and founder of NG Codec. We'll be talking about recent trends in live cloud video transcoding. Thank you, Oliver.
So welcome. Thank you for this opportunity. I'm going to talk for the next 45 minutes or so and attempt a live demo if the demo gods are favorable of me. So thanks to Nathan and to Vimeo for this great venue. I think we've had some great speakers. So I'm going to talk a little bit about what we do and what trends we're seeing in live video. So let's get going. So I thought it might be helpful just to give you a little history. Some people know us. We're a startup. We've been going about 7 years. It was 2012 when we incorporated the company. And we've delivered a range of products. They're kind of shown here as our progression has gone on. But what's a little bit unique about NG Codec is that we don't actually build software encoders. We build hardware encoders, and that's a little bit unusual. And in fact, at the time we were founding the company, everyone said that we were completely insane. Hardware was the way it used to be done, and it was now all going to be software. And we didn't actually believe that. We kind of felt that as codecs get more complex and as live grows in its usage, it becomes really difficult to do great compression efficiency in software. And so we went in the opposite direction, and that's what we've done. And so, we now have very sophisticated video encoders using many of the similar techniques that the other speakers have talked about, but we write them in a language that can be implemented in hardware, initially in field programmable gate arrays. These are Xilinx chips, and later in an ASIC. And the beauty of FPGAs is that field programmable means that you can change them. They're actually very, very similar to CPUs. You can load new images in. That means we can enhance our design. We started with HEVC, as you can see here. Then we did VP9. Now we're in the middle of doing AV1, and we're even doing 264. But with an FPGA, you can add all of that in. So, a lot of experience in the team, around 40 people, been working on this for quite a long time. And I'm going to share with you kind of where we see the market going and what our product does. So this is a simplified block diagram. It would be very common to all encoders. This is actually from our HEC variant, but most of our designs share a lot of these functionalities. In fact, the front part of the pipeline is basically the same. The look ahead, the analysis, the pre-processing, even kind of the mode selection to some extent are all pretty common. And then when you get into the middle parts and then the back end, when you talk about the actual transforms, the entropy encoding, those obviously become very specific depending on which format you're doing. Now, this in our design all runs in hardware, meaning that we actually use high-level synthesis. We write the design in C++, and we machine generate Verilog, which is the language of hardware. And then that gets delivered in. And in this pipeline, every portion of these blocks has to run in a finite amount of time. And that means it's fully deterministic. It will not vary on the complexity of the video or on the resolution. It always operates at the same amount of time. And so that means you get very deterministic performance. Also, not shown, but we do have a number of embedded microprocessors. They're relatively small. They're not doing heavy lifting. What they're there to do is to really make some of the low-level decisions. And so, this is really what we would think of as a state machine in hardware, but we actually have it programmable, and that allows us to have a lot of flexibility. So I'm going to talk briefly now a bit about the market trends that we're seeing. I mean, I think all of us are watching more video on our devices. So the graph on the left is really showing the amount of time that people are spending watching video, whether it's live or file-based, and that continues to go up. At the same time, if you look over the last 5 years and you look in the next 5 years, the mix of resolutions is also going up. People are watching more HD and even more 4K than they were in the past, and that trend is absolutely going to continue. And then finally, the codec mix is changing. You know, historically, 264 is still the dominant codec, but newer codecs like VP9, HEVC, and of course AV1 are gaining in traction. And these newer codecs have great compression efficiency gains, so they save bandwidth cost, they save storage cost, they improve the visual quality, the user experience, but the complexity is higher, meaning you need more cycles on CPUs and more of them. And so when you put all of that together, you can kind of see that the market is growing at around 50% annually in compound annual growth. And that means that by 2024, whatever you spend on delivering and processing video, it's going to be about 10x that by 2024. So it's a big, big problem, and that's where we think we can help. So this may be a little bit of a controversial slide, but I tried to take an impact for where do I think the mix of codecs is going to be over the next few years, specifically looking at the streaming market, i.e. delivery over the internet. And you know, I think, as we all know, 264 is still very, very dominant. It's 16 years old, but it's universally supported in nearly all browsers. And so it is the incumbent. And of course, you know, people like YouTube and Netflix and now Twitch are beginning to use and have been using VP9. And that's great. And HEVC for certain use cases like 4K is also being used. But I think what we tend to forget is that new codecs take time. The ecosystem has to be built out. You typically want mature encoders and wide decoder support. And so we are very bullish on AV1. I'll show you a demo in a sec. But we still think it's going to take some time. So on this graph, the green is AV1, and we think by 2023, it could achieve 40%, and that would be a massive adoption. But it's going to take some time, and as I said, you know, even next year, we estimate that less than 2% of all the streams will be in AV1. VVC or H.266 has a very uncertain history. It's really hard. Technically, it looks pretty decent, but I don't think they're going to solve the patent IP issues, meaning that it's going to have, I believe, challenges to be adopted, just as HEVC has had. Maybe the best we can hope for is that the original owners of the inventions in VVC also contribute them into AV2. Obviously, AV2 is not shown, but that will, towards the end of this timeline, probably be relevant as well. So, as I talked about, the costs are going up, and that's really a combination of the bandwidth cost, the storage cost, which is directly impacted by the bit rate that you can achieve of the encoder. And then you also have the computing cost, the total cost of ownership. That is, how many cycles and how expensive are those cycles. And that's really the encoding cost. And you know, a good encoding architecture and a hardware architecture can impact all three of these. So I think it's obvious. I mean, there are a lot of codec people here, but why does visual quality matter? And it really matters in two major ways. You know, for one, it's the economics for the service provider. If you're YouTube or if you're Twitch, you're delivering a huge amount of video. And it costs you some money to deliver that video. You also may have to store it. That also costs you money. But also as a consumer, a lot of people in the developing world have finite data plans, and they actually stop watching once that data plan is expired. And so if your business model is based on viewership with ads or other ways, you really want the best compression, because that will allow people to watch as much video as possible and have the best quality of video. The second is really this quality of experience, which is really about how good does it look. If you can have better compression, higher quality at a lower bit rate, you get better startup time, you get visual quality, you can get HD versus SD, you can reduce or minimize the amount of video stalls. And all of this contributes to the quality of experience. And as we know, you know, video is around 70% of internet traffic today and growing. So it matters to billions of people. This is just some public data from Huya, which is a Twitch of China. And because they're public, you can read their data. And just in one quarter last year, they spent $25 million just in delivering that video. And it went up significantly. It went up almost 67% because they were delivering more video and at higher quality video. Compression really has a big material impact to this. So when we look at the landscape of encoding, there are basically two major architectures. There's software on CPUs, which is the dominant architecture, and then there is hardware, where hardware can be FPGAs and ASICs. So if we talk about CPUs, CPUs are quite powerful. You have lots of cores, but they do have a fixed instruction set, and they have a very rigid memory architecture, hierarchical. You have on-chip memory, caches, level 1, level 2. And you basically have to adjust the algorithm, in this case a video algorithm, to that architecture. And you have to make compromises. You have to take shortcuts. And those shortcuts are more important when you have to do live video, because with live video by its nature, you've got to do 60 frames a second. And so you take quite a lot of shortcuts, which means the bit rate has to go up or the quality has to go down. The alternative path is to use hardware. Now, with hardware, you have a fully customizable architecture. You can implement anything you want. You actually program the hardware by changing the physical design of the chip, by actually wiring up the circuitry differently. Obviously, with FPGAs, we can do that in the field within a second, and we can keep changing it every second if we want to. With an ASIC, you have to kind of commit to a mask set. So it's something that you can't change all the time, although you can put some programmability in there with a processor. And so you're basically adjusting the architecture to the algorithm. And that has a massive advantage, and the advantage is efficiency. You can have much more performance, and hence power efficiency, in hardware versus software, where you do have more flexibility. It is inherently easier to write a piece of software, but as you can see on this graph, it's nowhere near as efficient. So those are the trade-offs. You can get software much sooner, it's quicker and easier to develop, but ultimately it has significantly less performance available to you, maybe an order of magnitude less performance. And so that performance is what you can use to do better compression. Fundamentally, every encoder is optimizing three things. They're optimizing the bit rate, the visual quality. What does it look like at that bit rate? And then the third is how much compute is available. How much searching, how much analysis, how much rate distortion optimization can I do? If you give me more compute, I can do a better job of those two. Hardware allows us to have more compute, and that's why we're able to do higher levels of compression. So one of the recent trends over the last few years has been to add FPGA instances into public clouds. Amazon started this about 2.5 years ago, but it's now been rolled out by many others. And so just like you can deploy a CPU and pay by the hour, you can do that with a GPU and also now with an FPGA. And that's how we deploy our technology, either in a public cloud or a private cloud, or even on-premise with an FPGA card, which is what I have here for the demo. So our basic premise is that CPUs are too slow to do live encoding. I mean, of course you can do it, but as you may know, with all of the software encoders, you have a number of presets where you're making those trade-offs of how good is the compression versus how many frames per second do I get. And in the case of X265, you have the fast and medium presets, which are typically what you can use for live, but you have the very slow, which really gives you the best quality. Ideally, you'd want to use the very slow, but it is too slow for live video, and so you can't use it. Similarly, if you use the Intel SVT, they have a number of presets, and about the best you can get if you want to do live on a really expensive $10,000 Platinum 8180, which is a high-end CPU, I think with 56 cores, is something like the M6 preset. Now, what you really want is the M1 or M0 because the quality would be better. Now, that's what hardware can do. With hardware, we can still do the 60 frames a second, but we can do it at these highly incredible compression efficiency. So why is it? And I've talked about this. It's really to do with the fact that, all modern encoders cannot do brute force. This doesn't matter if you're doing software or hardware. Reference encoders like the HM and the JM may do brute force, but any commercial encoder makes shortcuts. It has optimizations. We do that in hardware as well, but we have more performance to play with. So typically, we can do a full RDO, rate distortion optimization. In software, you have to create some shortcuts. And what we find is that you really have to combine the components of an encoder. It's not just about what are the tools that you need to support. Obviously, that's important. And you must be very comprehensive, support all the block sizes, all the tools, etc. But then you also need to have really good rate control, really good adaptive quantization. And you need to efficiently use those tools really, really well. And you basically need a team that has done this for many, many years. Fortunately, our team, many of them have over a decade or more of broadcast experience of building encoders. In many cases, they've built software encoders and hardware encoders. And there's a lot of details that I don't have time to go into, but we actually published a joint blog with Google and Twitch that's actually on the Twitch's technical website. Yoshi was one of the authors here, and that goes into some more of the technical details for why, in this case, the VP9, we were using a hardware encoder. So another thing I wanted to talk a bit about is VQ analysis, and we've heard a lot about quantitative, subjective, VMAF, PSNR, SSIM. I think they all have places, but ultimately, consumers look at video. And I think that that's the golden eye. The problem is it's difficult to do mean opinion scores. And so what I'm quite excited about is that we've started to use the tool called Subjectify, which comes from the Moscow State University guys. And it's a really cost-effective tool where you give them 20-second clips, and they crowdsource in a browser consumers to tell them which is better, the right video or the left video. And we did some benchmarking here, and you can see some results. I think this was at 2 megabits, and we were coming out significantly better. But I guess my general message here is that when you look at video quality analysis, separate the need to run a production system and see if things are going wrong. Clearly, at the scale that some of the cloud vendors operate, that has to be a quantitative tool, whether it's SSIM or PSNR. But if you're selecting an encoder that you're going to use for the next few years with potentially billions of users, you really need to spend some time looking at the video. And this tool, I think, in this, we spent less than $300, and we had like 100 different people looking at video and rating it. It's a really efficient way to go and see how the video is performing. And so I would encourage people to look at this tool. I think it's really cost effective and a really good way of evaluating what ultimately end consumers see, because they don't see BD graphs, they just see the video. So finally here, I want to just briefly kind of touch on how do we plug in. I mean, given that the world is software, FFmpeg or GeneStream or private frameworks are the dominant architecture that is used. So we provide plugins, in this case an FFmpeg plugin, that basically makes our encoder look like software. So the FPGAs physically plug in on the PCIe bus. And so by having a plugin, we're able to integrate quite seamlessly into the traditional transcoding framework. So as is normal, the demarcs, the audio, the remarks, the packaging, maybe even the DRM, those will all happen on a CPU. But the actual heavy lifting, that could be the video decoding, that could be the scaling, that could be the encoding, would all happen on the FPGA. And that would be under a simple FFmpeg or private API to make it very, very seamless to integrate into the workflow. So I'm going to attempt a live demo. Let's see how it goes. So we're going to switch now to, this is our eval kit. Maybe I should take this with me. Yeah, so this is a Ubuntu PC box, and inside we have a very small PCIe card that has a Xilinx VU9P FPGA. And this is a little controller app that we have written. And so I'm going to start with VP9. And so what we're doing is reading in a MP4 1080p file, and then I have it set up here on the encoder setting to do a traditional ABR ladder. So I think we're going to do 5 channels at different resolutions and different bit rates. All of this encoding will happen in real time on the same FPGA. We support up to 16 channels. And so I'm just going to hit the run button here. See if I can get it. So what it's doing now is programming the FPGA, starting the decode process, and then transferring the YUV video over to. And here you can see all the different bit rates. Now, we did have an issue earlier this morning that the monitor is actually being driven in interlaced, and my technical ability was not able to switch the Ubuntu books out of interlaced. So interlaced is here to rear its head, unfortunately. So there are interlaced artifacts coming up, that's just how the system is growing. But what you're actually seeing is a live VP9 encode. So let me just find the mouse. So, we're doing a 1080p, a 720p, 480, and I think 240. So all of this is happening there at different bit rates. Notice the 720p is at 1 kilobit, and all of that's happening live on the same FPGA. So that's VP9. What I'm going to do now is actually switch it to AV1. So let me just stop the encoder. And if you want to see here, this is the actual FFmpeg command line that the GUI is generating. And inside there, you can see that there's a NGC is the actual encoder. So basically, by changing the parameters on the GUI, it just generates a new FFmpeg command line. So what I'm going to do now is I could switch to our HEVC, but I think I'll switch to our AV1 encoder. So this is just a way of loading a preset. So let me load that. And now let's run it. So now the FPGA is being reprogrammed, and we're now doing AV1. Now this is AV1 is work in progress. So this is iframe only currently. The interside will have early next year. But this is a legal AV1 bitstream. QP25, you can see there at 1080p. We can also do 4K if needed as well. So we could save this bitstream to a file and then open it in Chrome or any other browser and show that it is a valid AV1 bitstream. So again, that's live, 60 frames a second, and we'll have the production version of that next year. And again, that will reuse a lot of the technology that we've built for our VP9 and HEVC encoders. It reuses the analysis, look-ahead block, the rate control, the adaptive quantization. So let me... Yeah. And of course, I could switch different bit rates, etc. But let me go back to the presentation now. Thank you. Yeah, so apart from the interlace guys killing me, the demo works, so I'm happy about that. Good. Thanks. So now I'm going to talk a little bit about TCO. When we look at the cost of encoding, this graph has quite a lot of data, but what we've done is we've kind of normalized the price per channel, assuming the cost of the silicon, the cost of the server, and the running costs, the power consumption and cooling. And when you do that around a Xeon E5, it comes out at about $800 per channel. And so I've used that as kind of the reference on bit rate. Now, some people do use for the tail, they use the Xeon E3, which is a QuickSync, the hardened encoder inside the GPUs. And it's very efficient from a cost point of view, but as people may know, the bit rate is about 45% worse than a good software encoder. And so it's kind of okay for the tail, but it's not really much use because the bit rate is so high. What we have today is our Vertex solution. This is the 16 nanometer FPGA. We estimate we're about 20% cheaper in cost for the same bit rate, but we can do substantially lower bit rate than software encoders for live. Now, obviously, for file-based, you can get very, very good quality with software. You just need to take a very long time, or you need to use a large number of machines. But we can do 60 frames a second, even at 4K, and we can also deliver that at substantially lower bit rate than what you can do with other live encoders. So maybe about a 20% lower bit rate. Next year, we'll deliver our Versal products. So the Vertex FPGAs are 16 nanometer. The Versal products are 7 nanometer, and these have been announced. They're beginning to sample from Xilinx. And they also have more efficiency, so they have more processing available in there that we can use to basically double our throughput. We believe we can go from a single 4K channel to 2 4K channels on the Versal product. So that brings the encoding cost down. And then in the future, we intend to deliver a hardened solution, an ASIC solution, because the design is basically the same. And obviously, an ASIC solution has drastically lower cost. So, the benefit that we can bring is drastically lower cost for live video today. But in time, once the ASIC is available, something like 6x or more lower cost, even for VOD, file-based, whilst continuing to improve the bit rate every single year. This is kind of similar outline. It's a bit of a messy slide, but it kind of shows how we started with a 1x density. We're now able to deliver 4x that density in the Versal products, 2x today on them. And we have HEVC and VP9 with 264 and AV1 coming, and then the ASIC in the future. And then I think my last but one, we like to kind of benchmark how we perform compared to other encoders out there. And obviously it's a complex, it depends what sources, what settings. But if we normalize it to X264 medium, our products, as you can see, are significantly lower. So, for instance, the Chestnut B encoder, which is what I'm showing here, is substantially lower, about 42% lower than that. And, with improvements that we have planned over the next couple of years, we think we can continue that improvement all the way down to maybe delivering the second or third generation AV1 encoder that we call Walnut, and being maybe 60% lower. So a lot of improvements, a lot of work to keep going. So last slide. It's a big market. Cloud video encoding is growing at about 50% per year. A lot of it is done by the hyperscalers. They do vastly more video encoding than traditional linear TV. And bandwidth and computing cost is becoming a major issue. We believe that fundamentally CPUs are just too slow, especially for live video, but ultimately even for video on demand once an ASIC is available. And instead of having to use these fast presets, we think you should be able to use the slow presets. And that's our strategy. And programmable hardware, although it's difficult to use, it takes a big investment. Once you have it out there, it can really deliver incredible bit rates, significantly lower than software, and also providing a nice roadmap to a hardened solution that can be orders of magnitude better. So that's a quick talk about recent trends that we see. Thanks very much.
Thank you so much, Oliver. Thank you for being here. We have a few questions from the audience. And if anybody has any questions, make sure you just raise your hand, and Preston will pop over. Let me... All right, I'll start with this one. It's, what do you think of the potential of neural networks to enhance performance of live encoding on the FPGA?
Yeah, it's a great question. I think it has lots of potential, but it will take a bit of time. Already, we are starting to do some machine learning techniques. So in the next release, our look ahead, one of the features of look ahead is scene detection, and we are already using an offline TensorFlow neural network to influence and help that scene detection algorithm to make it better. So we're beginning to use machine learning techniques, but there's a long way to go.
Great. You mentioned SVT needs a very expensive CPU to run at live speeds. How does this cost of a similar FPGA setup compare?
Well, pricing's kind of a bit of a black market, and it's out there. So it's kind of hard for me to comment a great deal, but the cost of a solution is the cost of the silicon, the cost of the server, and the cost of the operating, the power consumption, etc. And we know that the power consumption is significantly less than a high-end CPU. We also know that the pricing is less. I mean, the card I buy in here for around $2,000. So that's what I buy one of them off for. So I believe there are significantly lower costs, but pricing is something that the vendors kind of keep very close to their chest.
That makes sense, yeah. And Pankaj has mentioned, you mentioned writing C++ code and using machine conversion to VHDL. Is that really efficient?
Yeah, so we are one of the pioneers of a technique called high-level synthesis, which is exactly that. You write in C++ and you compile or machine generate Verilog. We believe it is. It is not as efficient as writing the equivalent of assembly. So in the hardware world, everyone kind of writes assembly still. They write in this very, very low-level language. And it does have more efficiency, but it takes 2 to 3 times as long. And so we've believed that it's the right trade-off. We haven't had the luxury, being a startup, to dedicate someone to take the same block and rewrite it in the Verilog assembly language. But our gut feeling is that we are giving up maybe about 10% of performance and maybe 10% of size, but we're gaining 200 to 300x productivity.
Great. Thank you so much. Just any other questions from the room while we're here? One at the front down here, and one at the back down there. We're keeping Preston running around. Here we go.
Okay, a couple of questions. The first one is, you mentioned that you would still need the CPU to run your pipeline, basically. In a box like that, are you using any CPU power?
We're not using any CPU power for the actual encoding. So everything to do with encoding is happening on the FPGA, including the rate control, because we have an embedded CPU. But it is a frame-level interface. So in a typical transcode, you would want to demux and do audio and feed the frames in and read the frames out. So those do need to happen on a CPU.
Okay, so does the cost of the solution that you mentioned include the cost of the CPU?
It does, but it's a very low-end CPU compared to
which is
high-end.
fair, right? Exactly. So, sorry, the other question is, How much complexity do you think AV1 will be bringing as compared to, say, your VP9 solution?
We're sharing quite a lot of code between them. Our first target is about 5% bitrate saving over our VP9 version. So we will not, in our first release, support the largest block size because that would add a lot more complexity. We might in the future.
Is that the same computational complexity or a little more?
A little more,
Okay.
but not much more.
Okay, cool. Thanks.
And then I think we just have one more question at the back. Yep.
Thank you. Yeah, that's just a question of curiosity. In the very beginning of your talk, you showed some numbers about codec adoption that look quite precise, and I just wonder how did you make those?
It's my opinion, having talked to a few people. By default, they will be wrong because nobody really knows. But I felt it was useful to, for us at least internally, when we're trying to prioritize what we make investments in. And the reason I wanted to share them was to get feedback. I think it's quite helpful for the industry to have some understanding of how quickly codecs can get adopted. So, yeah, that's. I mean, by default, they will not be correct, but I would welcome feedback because it's something that is important for us that make plans, but it's also really, really difficult to predict.
Great. Thank you so much for being here, Oliver. Let's all congratulate Oliver again. Thank you.
Thank you.